So last time we ended with annual motion. I'm going to say a couple more things. We talked about how the Earth's orbit is elliptical. So as it goes around here, then it spends part of the time here close to the sun, part of the time far from the sun. And we realized that what happens is that perihelion closer to the sun is in January, aphelion farthest from the sun. So it's how the sunlight hits Earth either more directly in the southern hemisphere, so that makes it summertime here and wintertime here, or more directly in the northern hemisphere, and so this is summertime and that's wintertime. Okay. So it looks like the orbit doesn't really matter. Well, actually, it does matter because gravity is stronger here than it is here. So the orbit speeds up and slows down. So it speeds up here, goes slow here, speeds up, slows down, speeds. So it actually spends more time here than it does here. Now, when it's summertime at aphelion, winter times here, at least in the northern hemisphere. Now, I will admit, this diagram is way elongated compared to what it really is. Really, if you were to look at the orbit, it'd look almost perfectly circular. Okay. But in this case, I've exaggerated to make a point. So one thing that we discover is we actually are going slower here and faster here. Well, when's summertime for us? Here. Well, that means it's going slower, so it takes longer here than it does here. Do you ever get the feel the summers are really long in Texas? Well, guess what they are? Because Earth is over here moving slow. If you were to count the days in the summer and compare them to the days in the winter, just look at the calendar. How many days in the summer, how many days in the winter? It's actually shorter in the winter than it is in the summer. And the reason is Earth is moving slower here and faster here. So we spend an extra week over here compared to over here. And so, yeah, it really is. Summers really are long in Texas. Okay. Now, timekeeping is also important because when we talk about time, we have to realize Earth is moving a little bit every day. And so Earth is rotating, but it's still moving. And so every day it's a little bit further. Now, if you were to watch the stars go around out here, then as the Earth makes one complete 360-degree rotation, then the stars have all repeated in the sky. So, but Earth has moved. And so that means that if you're standing here and the sun's, high in the sky, it's noon. By the time Earth has made one complete rotation, you have to turn a little bit farther to point back at the sun to get noon again. Well, what does that mean? Well, it means that the sky repeats about 4 minutes earlier than this, because this takes about a minute to go an extra degree. Now, this is just a tiny bit less than a degree, so it's not exactly 4 minutes, a little bit less than 4 minutes, but ballpark. So what is a day? People sometimes say a day is how long it takes to get from the sun from noon to noon. Okay, that's it. That's one way of defining day. But another way of defining day is the rotation of the Earth. Okay. So a solar day is noon to noon. Sun's high in the sky, high noon until high noon. A sidereal day is one actual rotation of the Earth. That's 23 hours, 56 minutes, and 4.1 seconds. So that's almost 4 minutes difference. So that means the sky repeats every 23 hours, 56 minutes, but it takes 24 hours to get from noon to noon. That's why the stars look like they rise 4 minutes earlier every day. And they set 4 minutes earlier every day. Well, in the old days, they kept track of noon and time by looking at the sun. So, in fact, noon was defined to be when the sun is on the meridian. And so we had ante-meridian, that's Latin before the meridian, post-meridian, that's Latin after the meridian, AM and PM. So AM, the sun is before noon, PM is afternoon. And so to the Romans, it actually meant this. So they actually counted down to noon. So 1 a.m. was 1 hour before noon. 1 p.m. was 1 hour after noon. Later, they switched clocks, so they all, the numbers progressively got bigger, small to big, rather than start big, go down to 0, and then back up again. Okay. But if you were to go out at noon, one thing you notice is the sun really isn't on the meridian at noon. Again, I was told the sun is straight overhead at noon when I was a kid. And so I had this experiment that I did. Part of a science fair project, I set up a stick and had the stick set up here, and I was going to show at noon, it had no shadow. Well, I discovered it actually had a shadow at noon, and worse, the shadow wasn't even shortest at noon. And so I borrowed my dad's level to make sure the stick was actually vertical, because I thought maybe that's a mistake, and I repeated my experiment, got the same results. And so it was like, what happened? Okay, the sun really wasn't directly overhead at noon, and it wasn't even on the meridian at noon. So what was going on? Well, first of all, remember we talked about how the Earth's orbit speeds up and slows down. That affects us. That means it's not exactly the same distance every day. So that means really the length of the day slowly changes over the course of the year. It's not exactly 24 hours from noon to noon every day. Now, in the old days, that didn't make a bit of difference to people because timepieces, clocks and watches and things weren't very accurate. They had to reset them every day. And so what they would do is they'd have someone, in the middle of town, and they would be watching the sun. When the sun got close to the meridian, they had this big iron ball on a spike, and they'd raise the iron ball to the top of a pillar on top of one of the tallest buildings. And as soon as the sun reached the meridian, they'd drop the ball and go thunk down, and everybody would set their timepiece to noon. They called that the time ball. And that became a standard, but every city and town had their clocks set up a little bit differently, and you had to reset it every day because the length of the day kept changing. Well, in the old days, clocks weren't very accurate. You had to reset them every day anyway, so this was not a big deal. But as clocks got better, this became more and more confusing. So what they started doing was they started finding the average length of a day over the whole course of a whole year, and they call that 24 hours. So what happens is that the local solar time is the time according to what the sun's really doing. Local mean time is the average time over the course of a year. Okay. Well, that changes a little bit. So what happens is that if you have a sundial, it keeps track of solar time, but you have to convert, add or subtract a few minutes, depending on what day it is, to actually convert from local solar time to local mean time. Local mean time is this clock time that runs 24 hours a day. And so there's this slight conversion that has to be done in there, and that's called the equation of time. And you can look up the equation of time. It says on these days add this many minutes, on those days subtract that many minutes. And even a stellarium would give you the equation of time. And so you can figure this out as to how to adjust from a sundial time to local mean time. Okay. So that's the first step. Next step we'll pick up in our next little mini lecture, and that's going to be civil time.